Let's return to this very famous sequence, the Fibonacci sequence. And how could we write a rule for the sequence? Recall that to get the numbers in the Fibonacci sequence, we add together two previous terms to get the next term. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so forth. So the next term in the sequence would be 8 plus 13 is 21, and then 21 plus, or 13 plus 21 is 34, and so, or I think the next 21 plus 34 is 55, and so forth. And that's how you get the terms in the sequence. Well, because we are referring back to previous terms, we would want to use a recursive rule. It turns out that using a recursive rule is very simple for the Fibonacci sequence. It's actually pretty hard to find an explicit rule for the Fibonacci sequence. So we're just going to look at the recursive rule. Now, I am referring back to two previous terms. So I have to start out with two given terms. I have to start out with a sub 1 equals 1 and a sub 2 equals 1 as my given. And then for n greater than or equal to 3, starting with a sub 3, then I use this rule. A sub n is equal to a sub n minus 1, that is the term just before a sub n, plus a sub n minus 2, which is the term before that. So let's see how this would work. For example, starting with a sub 3. A sub 3 is equal to a sub 3 minus 1 plus a sub 3 minus 2, which is a sub 2 plus a sub 1. Notice these numbers here, these subscripts, are not used to compute any numbers. They are just, these subscripts just tell me what position this term is in the sequence. So I'm looking at term 1 and term 2 and term 1, add them together, and I get 2. Now to do a sub 4, then it would be a sub 4 minus 1 plus a sub 4 minus 2, which would be a sub 3 plus a sub 2. So a sub 3 is this number, a sub 2 is 1, so it'd be 2 plus 1 equals 3. So that's how the notation works. So the rule itself is pretty easy for the Fibonacci sequence, but the set of numbers is a pretty amazing set of numbers, and I want to tell you a little bit more about them. And I want to start out by looking at this rectangle. This rectangle has a width of 21 and a height of 13, which are two of the Fibonacci numbers. Now, if we were to count over 13 squares here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let me double check that that is right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This gives me a 13 by 13 rectangle. Now, this rectangle next to it is a 5 by 13 rectangle. So both the 13 by 21 rectangle and the 5 by 13 rectangle have very similar ratios to each other. Now I'm going to count down, I'm sorry, not 5, this is 8, because 13 plus 8 is 21. Now I'm going to count down 8 and make an 8 by 8 rectangle, or 8 by 8 square. 1, 2, 3, 4, 5, 6, 7, 8. So here is an 8 by 8 square now, which leaves 5 here. And I'm going to count over to the right now and do a 5 by 5 square. Okay, so this is 5, which leaves 3 here now. And I'm going to make a 3 by 3 square, which would leave 2 here, and a 2 by 2 square, which would leave 2 squares of 1. So we have 1, 1, 2, 3, 5, 8, 13, and then 21, going around the dimensions of this special rectangle. So basically we can take any two dimensions and keep dividing down until we get all of the Fibonacci numbers. And I could have started my rectangle with any two Fibonacci numbers and this would work. Now once I'm in here, there's an interesting thing I can draw in here. If I start with where I ended up and draw a quarter of a circle in every square. So I'm kind of drawing, so think about just taking the radius of the side of the square and drawing a quarter of a circle inside every square. I get this really nice spiral that shows up in nature in a lot of different places. It shows up, that last piece doesn't look terribly good. I want to kind of fix that. Okay, there we go. It looks a little smoother now. That spiral shows up in a fern, like a baby fern that's all curled up and then it expands out into an adult fern. It shows up in certain galaxies. The pattern of the stars makes this Fibonacci spiral with these dimensions. And it also shows up very famously in this shell called the chambered nautilus, and it has, if you were to take this spiral, it has those same dimensions as that Fibonacci spiral. If we take that same triangle or rectangle pattern that I just drew, that forms the dimensions of the Parthenon. The ancient Greeks knew about this ratio, and they deliberately based a lot of their architecture on it. Leonardo da Vinci studied the golden ratio, and I'll talk about in a minute what the golden ratio is, but it's this ratio of Fibonacci numbers, and he used those same dimensions for the face of the Mona Lisa. Other places in nature this shows up are in plants. If we look at the spirals of the seeds in the middle of a sunflower, and we actually count the spirals going both directions, the spirals are Fibonacci numbers. You can see the same thing in pine cones and pineapples and certain types of broccoli and cauliflower. You'll see these spiral patterns, and the spirals are Fibonacci numbers. Now, the reason that's true is because God designed the Fibonacci numbers into the universe, because it turns out that when those spirals are Fibonacci numbers, the angles that separate the different spirals are just at the right angle so that all of the seeds or all of the petals or all of the leaves get the maximum exposure to sunlight, because there's always going to be overlapping, but the overlapping is just right so they get the maximum amount of sunlight, and it's all based on the Fibonacci sequence. The bones in your hand, the length of the bones in your hand, your arm, your height, all kinds of things form Fibonacci ratios with Fibonacci numbers. So, for example, the ratio of the bones in your hand, 2 to 3 to 5 to 8. My hand is almost exactly 2 centimeters, 3 centimeters, 5 centimeters, and 8 centimeters. A bigger hand might have bigger numbers, but the ratio would be the same. And all of this kind of boils down to this perfect number. We have those special numbers, pi and e. Well, there's another special number called phi. Phi is formed by taking the ratios of each successive pair of Fibonacci numbers. So if we take 1 divided by 1, 2 divided by 1, 3 divided by 2, 5 divided by 3, and so forth, and we keep going, that ratio approaches closer and closer to this exact value, 1 plus the square root of 5 over 2, or 1.618. This number is known as the golden ratio. And the golden ratio is called that because it's seen as a beautiful ratio that people naturally see as pleasing to the eye. So the ratio of the height to the width of the Parthenon, the ratio of the height to the width of the face, all of those are in that ratio phi. That ratio phi determines the angles that plants grow so they get maximum number of sunlight. So Fibonacci numbers are everywhere, and they're very interesting numbers. Google the word, and you'll find out lots more information than I've even told you about them.